All right, so welcome everyone to the IIT Bombay Virtual Commutative Algebra Seminar. We are very happy to have Yairon Cid-Ruiz from Ghent University in Belgium, and his talk is a continuation in some sense of the the talk last week, and he will speak on convex bodies and graded families of monomial ideals. This is a 1-hour talk. At the end of the talk, we will have question-answer session. So, Jairo, it is over to you now.
Okay, so it is a great pleasure to speak in this seminar, and I would like to thank the organizers for inviting me. And as you well said, I will my talk will be more or less kind of a continuation of the talk of Jonathan last week, and I will talk about some connections between convex bodies and the mixed multiplicities of graded families of monomial ideals. But I feel like this will be like the fifth talk in this topic of graded families of ideals. There was a previous talks by Kukowski and also by Jonathan and by Suprayo Das. So I will take maybe a more combinatorial and geometric point of view, and I will switch gears at some point. So I will talk about joint work with Jonathan Montaño, but I will also cover some joint work with Fateme Mohammadi and Leonid Mohammadi. Okay, so the first motivation, as Yuval was saying before the talk, is that there is somehow a quite interesting connection between mixed volumes and mixed multiplicities. So first, let me recall the well-known theorem of Minkowski. So suppose that you have a bunch of convex bodies, K1 until Ks, so S convex bodies, and for sake of simplicity, I will always put all these convex bodies in the positive orthant. The volume is invariant on translation. So now for any sequence of integers, lambda 1 until lambda s, I will use the following standard notation. So lambda times this vector k, math bfk, will be the following Minkowski sum. And k sub lambda will be the following multiset. So for I between 1 and s, I will take lambda sub I copies of the convex body k sub a. So this will be a set or a sequence where I allowed repetitions. Now, there is a classical important theorem by Minkowski, is that if you compute the volume of all these possible Minkowski sums, then this is a homogeneous polynomial of degree d in terms of these parameter lambdas, and this is called the volume polynomial. Now, by definition, when we write this homogeneous polynomial of degree d, we write that the coefficients are these integers, and we call them the mixed volumes. So here, following this notation, this is a sequence of convex bodies where you allow repetitions, no? And then we call that this mv sub d, that this denotes the mixed volume of this set allowing repetitions of convex bodies. Okay, so this is the definition of mixed volume. Now, to start with the connection between mixed volumes of convex bodies and mixed multiplicities of ideals, I need the following construction, it's a basic construction. The idea is that if you have a convex body in a d-dimensional space, always in the positive quadrant, you want to lift it up into a d plus 1 dimensional space where this convex body is in an hyperplane where all the vectors have the same weight. That's why we call it a homogeneous convex body. Okay, so just for notation, pi sub 1, let's denote that this is this projection from Rd plus 1 into the first d components, and that pi is just the computing the weight of a vector, so the sum of all the entries. So we choose certain integer such that the convex body, so this is for ease of notation, that the convex body will be inside. When you take, for instance, will be h sub k, and here also h sub k. So when you take this hyperplane in above, so this is in this hyperplane here, when you push it down into this triangle, we restrict that the convex body should be inside this, no? And then we define the homogenization of the convex body as, so you take like a cylinder of the convex body below, and then you intersect it with the hyperplane. So it's something like you're translating this convex body into one of these hyperplanes where all the elements have the same weight. Okay, so that's the homogenization of a convex body, and the idea is that now it's a convex body in a hyperplane where all the elements have the same weight. Okay, so first I will recall the original work of Schrum and Berma, which is actually was our initial motivation for this whole story, no? So, and the result is for lattice polytope. So a lattice polytope is the convex body of a bunch of integral vectors. So again, take a bunch of convex of lattice polytopes, and we are going to compute for each one of these convex lattice polytopes, compute a homogenization as before, and now for each one of these homogenizations is going to give you, of course, in a natural way, a monomial ideal. And actually, not only a monomial ideal will give you, but because of our construction, will give you a monomial ideal which is equigenerated. So, for instance, a j sub I will be all the elements in the hyperplane where is inside the corresponding homogenization of the convex body. Okay, let's denote by m the graded irrelevant ideal, but now it's a polynomial of v plus 1 variables. So very easy example. So if you take this convex body, so this simplex here, this is the convex hull of the vector 0, 0 in the two-dimensional space. Here 1, 0 and 0, 1. Now the homogenization will be now this one. So this thing painted in blue, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So given this convex body, the corresponding homogeneous ideal, in this case, will be just the irrelevant ideal. And then the initial story of our work was when we saw this work by Tron and Berma, and with Jonathan, we were quite surprised with this. And yeah, so they show that if you have an integer vector, as before, such that the total weight is equal to D, then we have that an equality between the mixed volume of the corresponding convex bodies and the mixed multiplicity of these monomial ideals, all of the same degree, that we are constructing with respect with the relevant ideal. I will not, as I said before, I will not enter into details about the mixed multiplicities. So this was defined by Jonathan last time. So you have a polynomial, and with this polynomial, they give you, so the length of j sub 1 to some n1 dot 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 j sub s n sub s, and then divided by the irrelevant ideal and send some n sub 0, and then so you compute this. This will give you a polynomial as Jonathan did last time, and then the coefficients of this polynomial are the mixed multiplicity. So this is we were surprised, but this result is for lattice polytopes, no? Now we wanted to do this for things that for arbitrary convex bodies, and then of course, if you have an arbitrary convex body, you will not be able to repeat this same program here, because to a convex body, it's something like it's irrational. There is no particular way of how to give some natural monomial ideals. And that's why we actually, our motivation for defining the mixed multiplicity of graded family of ideals was to be able to prove this theorem. And now, instead of taking lattice polytopes, let's take arbitrary convex bodies. So K1 until Ks are convex bodies in the positive order again. And now we choose again homogenizations of the convex bodies as before. Now let's recall that these homogenizations, they depend on these integers that we take. So remember, like we were taking a convex body here, we were making a homogenization. So was sorry for my drawing skills are quite poor. So we have here K tilde, and now what we are going to take is like a cone of this homogenization of the convex body, no? Okay, so we have this cone, and now instead of just having one ideal, we are going to get a graded family of ideals. And what we are going to do, so we have a cone in a d-dimensional space, we homogenize it into one of these hyperplanes or homogeneous. Now it's in a d plus 1 dimensional space, and we are going to take a cone. And now this cone, we are going to cut it infinitely many times, and then this is going to give you naturally a graded family of monomial ideals, where all of the monomial ideals are generated. So J sub I, this is a monomial ideal, a graded family of monomial ideals that depend on the convex body K sub I, and the n element of this graded family of ideals is generated exactly in degree n times the degree of homogenization that we chose for the convex body. Okay, so it's like the natural extension of this. And now the basic idea is that if you take this cone and now you are cutting and cutting and cutting all these lattice points inside this cone, in a certain way they are able to approximate as precise as you want the original convex body. Now, for sake of notation, let's denote the graded family of monomial ideals, where it's taking powers of the relevant ideal. And then we have that again. So we show that. So the first thing, so Jonathan last time he showed for you that this number exists. So this is a well-defined number. You have graded families of ideals, and for these graded families of ideals, where this is an arbitrary graded family of ideal, and this is a zero-dimensional graded family of ideal, there is a well-defined notion of mixed multiplicity that Jonathan described in depth last time. And now what we can prove actually is that the same result of Trung and Verma holds in this general setting. So if you have a bunch of convex bodies, arbitrary, you have this natural construction of making graded families of monomial ideas. Of course, if you have, for instance, something like a circle, bear in mind that these graded families of ideals will be non-Noetherian. So that's the construction of Jonathan last time. And somehow it's quite nice that the proof is extremely simple or compact using the results that Jonathan described last time. So just for notation, let's say that this K bar P is this is going to be a sequence of convex bodies. And now what we are going to do is to cut the convex bodies. Okay, and if you cut the convex bodies several times, and here you're projecting, so at each one of the steps, this number here is equal to this multiplicity, basically by using the result of Trung and Verma. Now, each one of these elements, you can prove, it's not difficult even by hand, you can prove that this limit is actually now equal to this limit. Now, instead of dividing by p to the d, you divide by p to the d plus 1. And now what you do is that you change the element, you take powers of the relevant ideal. And now here, we use a quite important result that, in my opinion, that Jonathan described last time, that which is the volume equals multiplicity formula. So remember that for the volume, so he described that certain multiplicity of a graded family of ideal was the same as taking this normalized limit of bearing on each one of the elements of the graded family of ideals. Okay, so here is the result that Jonathan described last time. This number is well defined. And now here, the main step, actually our main tool is really using the volume equals multiplicity formula that Jonathan described last time. So up to the moment, this is what I wanted to say about the connection between mixed volumes and mixed multiplicities of graded family of ideals. If there is any doubt about this statement, please, and if not, we can continue. Okay, so I will continue then. So I want to talk about this notion of mixed multiplicities of arbitrary graded families of ideals. There is some noise. Oh. Okay, so I want to cover now a little bit of the work that I did with Leonid Monin, with Fatima Mohammadi and Leonid Monin. So first, recall what are the multiplicities of just a graded algebra. So suppose you have K a field, R is a standard graded finally generated algebra. Then we all know that exists a Hilbert polynomial, and that the the coefficients of the highest degree term, this coefficient is called the multiplicity of the algebra. Remember that we can alternatively compute the multiplicity of an algebra taking this limit, no? So you take, you multiply by d minus 1 factorial, and then you take this limit divided by n to the d minus 1. Because this is a polynomial, this will give you the multiplicity. Now, the geometrical counterpart of this story is that if K is an algebraically closed field, and then you have that X is the corresponding projective variety, then the multiplicity is just the same as the degree of the projective variety. And how is defined the degree of a projective variety? So the variety has dimension d, and then you choose an m minus d minus 1. Sorry, the projective variety has dimension d minus 1, so you choose a general linear subspace of dimension m minus d minus 1, and then you just count the points on that intersection. Okay, so that's the notion of degree that we all know. General, if you, this is like there is a parameter space, and then you choose a dense open subset in that parameter space. And now, but I want to talk what about for not finally generated algebras. So as before, suppose that K is an algebraically closed field, S is a finally generated field extension of K, and let's choose this polynomial ring in this way. Now suppose that this polynomial ring is a standard graded, where the degree of the variable is 1. Okay, now choose again S, a finally generated standard graded K algebra, and here we are interested now in a subalgebra of this algebra S, with the condition that this algebra may not be finally generated in principle. And just for the sake of simplicity, we will always assume that you can regrade the algebra. So let's assume that in the graded part 1, the algebra is not 0. Now, this algebra is called an algebra of almost integral type. And this is basically the type of algebras that was very interesting in the work of Kave and Kovansky and Lazarfeld and Mustata. And the idea is that for any kind of these algebras, you will associate first evaluation, and then from this evaluation, you will associate certain semi-group. So suppose that the field is algebraically closed, and you have evaluation. If the field is algebraically closed, then we can show that this valuation is a valuation with one-dimensional leaves. The dimension is that the idea is that all the possible elements that they are going to have exactly that value, the dimension as a K vector space will have at most dimension 1. And the leaf of this valuation, you can think it in the following way, no? So you take this vector space because it's evaluation. So you take, for any n, you will take all the elements inside the field so that the value is bigger or equal than n. And then you quotient out by all the elements that they are going to have value exactly bigger than n. So this will have a structure of vector space, and this is what gives you the idea of what is the vector space of all the elements that have exactly one value, no? So this lemma says that if you have, in this setting for an algebra, for any field, if you have that the field is the base field is algebraically closed, then you can find such evaluation with one-dimensional leaves. Now, in this setting, you can define the value semigroup of the algebra, which is, so for each graded part of the algebra, so you will take, this will give you a sub-semigroup of z to the r times n, no? So, and the idea is that for each graded part, you will take the vector, which is n, and then you will take the valuation of this non-zero element. So this will give you, since it's an algebra and you are taking evaluation, this will give you naturally a semigroup of this type. Okay? Then what's the main result in this area is the following. So that if you have this, so we started with an algebra of almost integral type. then we define a subset as a semigroup. Now, this semigroup, naturally, when you take the cone, will give you this cone, and the notion of the convex body, or so the Newton or concave body of that algebra will be that you take the cone of that semigroup, and then you intersect at the hyperplane on 1 on the last component. So the last component will give you like the graded parts of the algebra. That's why it's important here to assume that the algebra, the graded part 1, is non-zero. Okay, and then there is a result by Kave and Kowalski that the asymptotics of the algebra is basically equal to the volume of the Newton concave body divided by the index. The index is an integer that it's in terms of certain the index of certain groups, but let's not enter into that detail. It's an integer. So what it's more important is the volume of the convex body. And so the main idea is that there is a strict relation between like the asymptotics or multiplicity of any algebra, not any algebra, like algebras which are not necessarily finally generated, that with the small conditions that they are of almost integral type, and the volume of convex bodies. So we have this slogan, and what I want to talk about this because the techniques that we use in the work with Jonathan in the end are using just this type of results. So the asymptotics of an algebra of almost integral type is given by the volume of the Newton or concave body. So let's see an example. So if you have K is a field, and then you have F is this field of rational functions in one variable, let's construct the following algebra. So we'll take I between 0. For each n, you will take the lower, the floor function of n times the square root of 2. This will give you a subalgebra here. It's easy to check that this algebra is not going to be finitely generated, but the nice thing is that this algebra is of almost integral type. Why? Because this algebra, which is non-Newtonian, is inside this nice algebra S, which is just a K of t, xt, x squared, and xt. Now, by hand, even here, we can take the most basic valuation that you might think of, that the valuation of xi goes to I. And so we have the following semigroup of the algebra R, which is n bigger or equal than 0, and then I between a square root of n and n times a square root of 2 lower. Now, by hand, you can compute this, that the limit or the asymptotics of this algebra is going to be equal to a square root of 2, no? But actually here, we can see that, so all these points in red, also this should be also a point in red, is the semigroup of the algebra, no? Now, when you take the cone, it's going to be this line that I'm painting here in purple. Now, the cone of the algebra S is going to be this algebra, this cone here that is painted in green. So the cone of the algebra is this thing. Now, if you intersect this cone at the graded part 1, will give you this line. In this case, dimension 1. The convex body, the Newton concave body, have dimension 1. The length of this thing is a square root of 2, and so this is the theorem of Kave and Kowalski and Lazar-Fels and Mustata. And now, why do we care about this? So actually, the original interest of Kave and Kowalski and Lazar-Fels and Mustata was like studying the section ring of a Cartier divisor in a projective variety. The section ring is the following: you take global section of all the possible twistings of the divisor, and typically this section ring is non-Newtonian. And there is a lot of literature about this. There is also more algebraic. The symbolic Riesz algebra is well known that is typically non-Newtonian. Also, another type of non-Newtonian things are filtrations that come from valuations. Also, from a more algebraic point of view, there is like computing the epsilon multiplicity of an ideal. This is the standard notation, the standard one of the standards extension of mix of Hilbert-Sandwell multiplicity for ideals that are not zero-dimensional. So there is really a lot of interest of why studying algebras of almost integral type. And now, what's the objective that we want to discuss here is that we want to address like the multigraded story of this work of Kave and Kowalski and Lazar-Fels and Mustata. So we want to study algebras of almost integral type in a non-Netijan setting. And so we will see that we will define and study a volume function for any algebra of almost integral type in a multigraded setting. We will relate this function, this volume function, to a global Newton or concave body. Will be an extension. Also quite interesting and related to the work with Jonathan is that we want to see when this volume function is a polynomial. For instance, we saw with Jonathan that if you analyze Riesz algebras to study this, the Riesz algebra of these graded families of ideals, the thing is going to be a polynomial. We will see one application. So more or less following some techniques from Kutkowski, we'll show that we can drop the assumption that the field is algebraically closed. And something quite important here is that we will relate that directly the asymptotic of this volume function with the curl dimension of the algebra, and not just the dimension of the Newton and concave body, because in the original work of Kabe and Kovansky, it's given in terms of the dimension of the Newton or concave body. Okay, so our interest here is really to cover the whole multigraded version of this beautiful theory of Kabe and Kovansky and Lazarfeld and Mustata for all algebras of almost integral type. And we will see that this has a direct relation for mixed multiplicities of graded families of ideals. Okay, so again, I need to recall some basic facts. So even in the standard graded case, so suppose you have an algebra, an NS algebra, which is a standard graded. So let's know that K is a field. We have this algebra, NS graded. We say that the is a standard graded if the algebra is generated by elements of total weight equal to 1. So it's generated by elements of degree 1, 0, until elements of degree 0, 0, 0, 0, 1. And again, let's fix. So I will fix this notation for the rest of the talk. And my talk will be to show you that you have also like a theory of mixed multiplicities for these general classes of algebras of almost integral type. So then the beginning of this is a result of van der Waerden in 1929, and that in this graded setting there is again the notion of Hilbert polynomial. Now this Hilbert polynomial is going to be a homogeneous polynomial of total degree d minus s. So the grading is n to the s. Okay, and so this n is a vector n1 until ns, and this d is going to be d1 until ds. And you can show, so even van der Waerden a long time ago, he showed that the Hilbert function is equal to the Hilbert polynomial when the vector is bigger or equal than the zero vector, and this means that each ni is big enough, so it's bigger or equal. It's a very big number. Okay, so then you have this notion of Hilbert polynomial by van der Waerden. And now in this multigraded setting, you have, instead of just one multiplicity, you have an array of mixed multiplicities. And so this polynomial, the elements of largest degree are going to be non-negative. And you say that when d, the vector has the maximum possible weight, you define this integer here, non-negative integer in the multigraded Hilbert polynomial as the mixed multiplicity of the algebra of type D. Again, so there is a geometric side of all this story. Now, if you have that the field is algebraically closed, and there is a natural way, so I'm writing here multiproduct to a multigraded algebra, there is a natural way to associate a multigraded, a multi-projective variety here in this product of projective spaces. So let's assume that it lives inside here. And now, then the mixed multiplicity of type D is going to coincide with the following multi-degree. And this multi-degree, the notion of multi-degree, is the natural extension of the notion of degree now into a multigraded settings. Okay, so the multi-degree of type D. So remember, D is a vector D1 until ds. And here what you do is like you intersect your variety with the product of general linear spaces, where the linear space like L sub I lives inside the product of projective space M sub I, and is a general linear subspace of dimension Mi minus Di. So what we have seen until now, we have seen that for algebras of almost integral type in a single graded setting, there is a theory of algebras of almost integral type, and the asymptotics of this kind of algebras is ruled by the volume of certain convex bodies. Okay, now I want to recall the notion of mixed multiplicities for multigraded algebras, and now what we want to do is to see how to relate certain combinatorial object or certain convex body to the asymptotics of multigraded algebra, which is going to be of, we will define also what the notion of almost integral type in this setting. Okay, so we have the following data that we will use. So K is a field, F is a finally generated field extension of K. So I forgot before, really, this is really not a restriction at all, because you can restrict to a certain subfield, because in the end, everything lives inside some algebra which is finally generated. Okay, so now K is a field, F is a finally generated field extension of K, and now let's take the following polynomial ring, which is a standard graded. So the degree of the vector Ti is going to be equal to the elementary vector inside n to the s. Okay, so the variable T1 has degree 1,000, and the variable T sub s has degree 0,0,0,1. Now let's take an algebra which is a standard graded finally generated K algebra. So we remember, algebras of almost integral types are algebras that are not necessarily finally generated, but they live inside something that is finally generated. Okay, so we do, because we need, in the end, we need some boundedness condition for the complex bodies. Okay, so take an algebra which is standard and S finally generated, okay, and now take a d-dimensional algebra inside this V. Let's assume, again, just for ease of notation, that the algebra at the vector, so in the graded part 1,0,0 is non-zero until the graded part 0,0,0,1 is non-zero. Okay, and now this is the direct extension of the notion of algebra of almost integral type into a multigraded setting, and we call that A is an NS graded algebra of almost integral type. And this is really the object that we want to study now. And bear in mind, if you want to study mixed multiplicity for ideals, what you need to do is to take that A is equal to the Ruiz algebra of like a bunch of graded families of ideals. Okay, in a natural way, if you do this kind of problem, you can study the mixed multiplicities of graded families of ideals. Okay, so, but now here, what's the function that we want to study? So the function that we want to study is something that we call the volume function. And here, what we are going to take is that for any n between 1 and s, let's take always positive integers, you will take the asymptotic of in the following ray, no? So we will remember, this is similar to the construction that Jonathan did last time. So you were fixing like a bunch of ideals, like a, and then you were taking the whole ray, no? And so here, like the geometrical notion of dimension here will be like the crude dimension of the algebra minus s. So we take n divided by q, and this is the volume function. Remember, in the standard gradient setting, like in the setting of van der Waerden, this function will, if you have the Hilbert polynomial and you compute this, this the Hilbert function of this algebra when all the ni's are, so when n is big enough, because all the ni's are positive, this function is going to be is going to coincide with the Hilbert polynomial. But now, since we are dividing by n to the q, so we stay only with the homogeneous part of maximal degree of the Hilbert polynomial. So indeed, this kind of volume function deletes all the the noise from the Hilbert polynomial and stays with the part that we want, the mixed multiplicities of the algebra, no? Okay, so if you want to study like a volume function of an algebra, so this is more or less the natural way of going, and this is the algebra. This is the function that we are going to study. So we are fixing a multigraded algebra of almost integral type, and we want to study this volume function. Okay, is there any doubt or question until now? This is the way that we want to embark. Okay, so I will continue. So we want to study this function given an algebra of almost integral type. And this is like computing the asymptotic of the algebra for all the possible rays in this multigrading. Now we have this result that follows more or less using techniques started by Kubkowski, because this whole theory by Kabe and Kovansky and Lassenfels and Mustata was really valid over an algebraically closed field. But actually going from an algebraically closed field to an arbitrary field is kind of it's not like a trivial problem, because we saw that when the field is algebraically closed, you can always find valuations which are with one-dimensional leaves. But here, if you get any field, now you can have leaves with bounded dimension. We can show the following, that there is evaluation from the field. Remember that everything lives inside this field and taking that polynomial ring. There is evaluation from the field into Z2R. Typically, this R is the transcendence degree of the field, but let's not enter into details. Now, and there is also an integer, so that all the leaves, all the possible leaves are going to be bounded by this integer that we chose. And again, so the leaf is some way to say the vector space of all the possible elements that have certain value. Okay, so in the algebraically closed setting, we have that you can only find you actually can find leaves with one-dimensional leaves, but in the general setting, the best you can do is to find leaves with evaluation such that the leaves have bounded dimension. And now remember that if the leaves have bounded dimension, you have like it's like a one-to-one correspondence in a sense, no? Because each element has like one value, and then it's like they map correspondingly, like bijectively, with the semigroup that you are considering, no? But here, since you will have like the leaves can have so they could be like technically two elements with the same valuation in terms of as the dimension of a vector space. So we define the following integer, which is the maximal length of the algebra with respect to V, to the valuation, and which is the maximum of all the possible so the leaves, and then you intersect with the algebra, and this is going to be smaller or equal than this integer. So this makes sense to compute this maximum. Okay, so we have this integer. Now, how we will define the value semigroup of the algebra? So we will do exactly the same that before. So before here S was 1, no? But now we will grade this semigroup of N corresponding with the gradient that we are using, and then you take all the elements that are non-zero, and then you take the valuation of those elements. Since you are taking with respect to the valuation of this algebra, this is going to be a semigroup. And now here we call the global Newton or concave body of this algebra. You take the cone of this algebra. And this is somehow tricky notation, because we say global Newton or concave body, but this is not a body, it's actually a cone. but here we are following the notation of Lazarsfeld and Mustata that they study multigraded linear series, which is like studying several divisors on a projective variety or all of them at the same time. So we're following the notation of Lazarsfeld and Mustata. And here, if you have this global Newton or concave body, this is going to live inside the product of R to the R times the positive orthan, so here, of to the S, no? Now here you have a projection into the first component and a projection into the second component. And for any element X in the second component, we say that the corresponding fiber is going to be taking the pre-image of that point here and then intersecting with the global Newton or concave body. Remember, this again will be like the right generalization of the work of the original work of Kabe and Kovansky and Lazarsfeld and Mustata. Why? Because remember, if S is equal to Y, equal to 1, so in the standard graded, in the single graded setting, we were saying that was equal to the cone, so the cone of the algebra, and then you were intersecting with so R to the R, and then in 1, no? So before the convex, the Newton or concave body was actually the fiber of this global Newton or concave body on the point 1. So remember, let's go, sorry for going back, but just to see that is in the end. So here, you see here that if you are going to take these Newton or concave bodies, they are exactly certain fiber with respect with the second projection of certain cone. Okay, so sorry. So we have here the following. So we have the following now. The following three ingredients. No, you are given an algebra of almost integral type, which is multigraded, and now you have the length of the algebra with respect to the valuation. You have the semigroup. You have the global Newton or concave body, which is actually a cone. And now you have here two natural projections. Taking into account the second projection, this is going to give you a fiber, and this fiber is actually a convex body. And the main result that we have is actually that everything works nicely in this setting. So suppose you have an algebra almost integral type with this assumption, just for ease of notation, that Q is equal to the crude dimension of the algebra minus S, so the grading of the algebra. Then the first thing that we can show is that this function exists. Okay, so in the quadrant, so this function, the volume function that we are studying is a well-defined function. And now actually what is related to the previous setting is that actually this function extends uniquely into a continuous function that is homogeneous of degree Q and log concave in the positive orthan. And now this function, when you take for any x here, what you do is like you take the value of the function, so f of that x is going to be actually equal to the volume of the certain fiber divided by the index. Again, the index is an integer, the index of certain groups, now times the length of the algebra. So if the algebra is a field is algebraically closed, so this L is just 1, the length of the algebra, one-dimensional lift in the setting. And now if you have S equals to 1, so the classical setting of Kabe and Kovansky and Lazarsfeld and Mustata, you have here that this is exactly the fiber at 1, no? So this is the volume of the Newton concave body. So our main result here is actually that the volume function of any algebra is going to be well defined. So that's the first step. And not only that, it extends uniquely as a quite nice function, is a homogeneous of degree Q, which is log concave in the positive orthan. And you have a complete description of this function in terms of the volume of the global Newton concave body, and now computing certain fibers. Okay, so let's see a simple example. So again, I like to use these examples with the square root. So take f, a field of rational functions in one variable. And now let's define the following function, alpha in 1 and 2. Now we define the following family of graded vector spaces, which you take all the formal combinations of x1, x to the xi, and then I goes between alpha and 2n plus 1. So this lives inside here. Now you can check that this A is naturally an n-graded algebra, k-graded algebra. So you define all these vector spaces, and if you take all this direct sum, this is naturally an n2 graded algebra. Is non-Euclidean, but again is of almost integral type because you can check that it's inside this other algebra B. So it follows from our definition that A is an n2 graded K algebra of almost integral type. Then the volume function in this setting you can check by hand because you have an explicit formula that this is equal to 2n plus 1 plus n2 plus n2 minus 2 square root of this thing. So you here see that this function can be actually quite difficult, can be a quite complicated function. It's not a polynomial, so the best that we can say is that it's homogeneous of degree 1 and that it's log concave. Okay, so now in these minutes that I have, I want to address the question of when. So I want to find a wide class of algebras for which the volume function, so this function that we are defining, is actually a polynomial. And our answer for this is actually is a whole, actually not so small family of algebras that we call algebras that have a decomposable grading. And we say that an algebra has a decomposable grading is the algebra in the graded part n1 until n2 is actually equal to the product of the elements in each one of the part, no? So a typical example of an algebra with the composable grading will be like the multi-Riesz algebra of a bunch of ideals, or even a graded families of ideals. Okay, so we have this definition of algebras with a composable grading, and then we have this other result which says that indeed, if you have an algebra which is of decomposable grading, then so if A is an algebra with decomposable grading, again, almost integral type and multi-ns graded of dimension D, where Q is equal to D minus S. So then there exists a non-negative, an homogeneous polynomial with non-negative real coefficients, so that actually the function is equal to that polynomial. So we have a whole array of graded algebras of almost integral type that they have the volume function is equal to a polynomial. Typically, will be, remember the example, what Jonathan was covering. If you have a Riesz algebra of a multi-Riesz algebra of a graded families of ideals, this will be a nice example of an algebra with a composable grading. Okay, now, so if you assume that the algebra of almost integral type of dimension D, ns graded, has a decomposable gradient, we can do the same as before. You can, so now the volume function is actually a polynomial. You can write it in this way. And now the coefficients, you say that the coefficients are just the mixed multiplicities of the algebra. Okay, so for multigraded algebras of almost integral type that have a decomposable grading, you have a notion of mixed multiplicity. Typically, these mixed multiplicities will be arbitrary real numbers. That they don't need to be rational integers and not even rational. Now, actually, so I'm falling short on time. So we have a description of when the mixed multiplicities of these algebras with the composable grading are positive. So we have an explicit description. So the idea is that you have this algebra and you are going to project into all the possible subgradings of the algebra. Now, if you check these inequalities, then you have an if and only if condition for the positivity of this mixed multiplicity. And again here, the idea is that this kind of algebras with the composable grading, you can approximate them by algebras which are standard graded, and then we can use a work with Castillo Lee, Binglin Lee, also Jonathan Montaño, and Naisen Chang, where we gave a complete description of when multi-degrees are positive. Okay, so for these algebras of almost integral type with the composable grading, you can characterize when an algebra, so you have this characterization for the positivity of the mixed multiplicities. Just a geometric application. So if you have a projective variety and you have a bunch of character divisors, then the section ring is going to be a multigraded algebra. A subalgebra of this multigraded section ring is going to be called a multigraded linear series. Now here, this Q that we were denoting in this case is going to be called the Kodaira-Itaka dimension of W. And then it's like, of course, this is an algebra of it's going to be an algebra of almost integral type. And we basically have the same result. And let me say that these two items, so 1 and 2, when the field is algebraically closed and with some additional small conditions, this actually was done by Mustata, by Lazarsfeld and Mustata. So if you have any field, now you can obtain this result. And now we also have a bunch of families of graded linear series so that the volume function is a polynomial function. Okay, so this is one application. And so I started convex bodies and graded families of ideals. So now I'm going to get back to that topic. So you have a bunch of convex bodies. So remember, this was denoting the volume polynomial of the convex bodies, and the coefficients of that volume polynomial are called the mixed volumes of the convex bodies. Now there is a well-known formula that you can find in any book of convex geometry. Is that people in convex geometry, they have a characterization of when mixed volumes are positive. And now here we have using these algebraic techniques, we can give an alternative proof of this result. I mean, this is well known, but it's somehow interesting that you can use these algebraic techniques to recover proofs in complex geometry. So suppose that, so for the integers for the vectors of maximal weight, so remember, so then there is this characterization that the corresponding mixed volume is positive if and only if for any subset of 1 to the s, you have the following inequality, so that d sub j1 until d sub jk is going to be strictly smaller than the dimension of the sum of the corresponding convex bodies. Now we have an alternative proof, which is actually just 2 steps, quite small. Like in the beginning of this presentation, I show you that mixed volumes of convex bodies is just the mixed multiplicities of graded families of monomial ideals. And in the previous slide, I show you that we can characterize the positivity of mixed multiplicities. And so joining these two things, you recover when mixed volumes of convex bodies are positive. And that's all what I wanted to say. Thank you very much.
Thank you, Yairon. Thank you very much for your interesting talk. We are open for questions now. Okay, I had a question about algebras of almost integral type. You said that we can associate mixed multiplicities, but do they satisfy Minkowski inequality? Hello, Yairon, can you listen? Can you hear me?
Yes, they satisfy.
Yeah, so since for very general algebras, we have a notion of mixed multiplicities, and we know when they are positive. So if they are positive, do they satisfy Minkowski inequalities?
So actually here, to prove that the function is log concave, What we use is the Brun-Minkowski inequalities of mixed volumes of convex body, and it's well known that when you have Brun-Minkowski, this implies low concavity.
Okay. Yeah. Okay. Yeah.
Thank you for the question.
Yeah. Yeah, since these many of these results are valid for arbitrary graded families.
Yes.
So suppose you take a graded family of the integral closure of powers of an M primary ideal.
Yes.
When the ring is in a local ring, when the ring is analytically unramified, this graded family behaves nicely, because one can associate a Hilbert polynomial, normal Hilbert polynomial, with this graded family. But when the ring is not analytically unramified, one can produce graded families so that the Riesz algebra is not Noetherian.
Yeah, so you can have now in this setting you can study one of these volume functions and see what happens.
Exactly, yes? Exactly. Whether it does exist and know what does it mean for the local ring. Yeah.
So and then if you really get like bunch of graded families and you can study the multi-Riesz algebra, so again you can define the mixed multiplicity.
Right.
Of this algebra.
Yeah. So, but have you calculated these for symbolic Riesz algebra when it is not Noetherian?
No. We have not tried that.
But they do exist. But they do exist, right?
Yeah. That's always interesting, but we have not tried that.
Yeah. Okay. Are there other questions? Yeah. I don't see any further questions. So let us all thank Yairon for his very interesting talk, connecting many things in geometry and algebra and convex geometry. So Yairon, thank you very much. Yeah.
Okay, thank you.
Yeah, we will close the meeting and